Okay, so now we've got a DFA, and what we have to do is you have to work out, are any states of the DFA equivalent to each other? And if they are, can we redraw it in such a way that it is minimal? So we can use the algorithm that we saw in the lecture slides. And how that algorithm works is you basically write all the states into two groups. Start off with the final states and the non-final states. So the final states are S0, S1, S4. So there's the final states, and the non-final states are S2, S3, S5. So what we do is we have to check which group they transition to under a particular character, and split group based on which states, based on which group they go to. So if we try, say, splitting on a 1, S0 under a 1 goes to the other group, S1 under a 1 goes to the other group, S4 under a 1 goes to the group, so unfortunately no splits there. S2 goes to S3, so it goes to the same group under a 1. S3 under a 1 goes to S4, which is in the other group, so that will S2 and S3 will split. And S5 under a 1 goes to S3, which is in the same group. So that isn't enough evidence to distinguish S2 from S5, but it is enough to distinguish S3. So we have no splits in the first group, but we split off S3. And we repeat this process until we get no splits for either character. So let's try again. And what we can do is we can try to tactically choose characters to split on, so we'll guarantee to get splits. So let's have a look. S0 and S1 and S4, they're all in the same group, but S2 and S3 are no longer in the same group. So if we check on a 1, S0 goes to S2, S1 goes to S2, so no splits there, but S4 goes to S3, and we know S2 and S3 are non-equivalent. So when we split on a 1, if we split on a 1 again, we can break off S4. So S0 and S1, they stay together for the moment. We don't have sufficient evidence to say they're non-equivalent. Okay, what about the last two states? S2 and S5. S2 goes to S3, which is this group here, and S5 under 1 goes to S3. So they both go to this group here under 1, so no split. Okay, so we got a split, so we'll try again. S0 and S1 under 1 go to S2, so that won't work. S0 and S1 under a 0, S1 goes to itself, S0 goes to itself. So it looks like we're never going to be able to split this group up, no matter how hard we try. So what about the other case? S2 and S5. S2 under a 0 goes to S1, S5 under a 0 goes to S1, so we can't split there. S2 under a 1 goes to S3, and S5 under 1 goes to S3, so again we can't split. So it looks like no matter if I try either 0 or 1, in either case, we won't get a split. So technically what you're supposed to do following the algorithm is try all the characters. So you try a 0, nothing happens, and then you try 1, and again nothing will happen. So then the algorithm terminates, and we can declare that S0 and S1 are equivalent, and S2 and S5 are equivalent. Okay, so these are my equivalent states. And yeah, how do we know the algorithm's terminated? Because I tried all the possible characters, I got no more splits. So now what? So I can redraw this diagram and eliminate some of the states. So I'm going to eliminate S1, and I'm also going to eliminate S5. And so what we can do is we can redraw the diagram using only these states, and we sort of, if something would go to S1, we send it to S0, and if something would go to S5, we send it to S2 instead. So let's draw the diagram. Final states stay final. Under 1 goes to S2. S2 goes to S3, okay. Under 1 and under 0, so I'm just copying the diagram until I try to copy a transition where I can't. So S2 under a 0 goes to S1, but there is no S1, so I send it instead to something equivalent, and S0 is equivalent. So under a 0, it goes to S0. Okay, what else can we draw? What S3 does. So for 1s, it bounces back and forth between S4 reader 1, reader 1. S4 under 0 goes to S1, but S1 no longer exists, so we'll send it to S0 instead. Is that all the transitions? Every state has an outbound 0 and 1. So yep, this is our new DFA that recognizes the same language but is minimal.